So far, we have analyzed stability for a fixed system. But in practice, we design controllers with adjustable gain k. As k changes, the closed-loop poles move in the S-plane. The root locus is the plot of all possible closed-loop pole locations as k varies from 0 to infinity. It is one of the most powerful tools in classical control design. Consider a unity feedback system with open loop transfer function k times g of s times h of s. The closed loop characteristic equation is 1 plus k times g of s times h of s equals 0. The roots of this equation are the closed loop poles. As k changes, these roots trace paths in the S-plane. Those paths are the root locus. Rule 1. The root locus has n branches, where n is the number of open loop poles. Rule 2. The branches start at the open loop poles when k equals 0. Rule 3. The branches end at the open loop zeros when k approaches infinity. If there are more poles than zeros, the extra branches go to infinity along asymptotes. Rule 4. The root locus is symmetric about the real axis because complex poles always come in conjugate pairs. Rule 5. A point on the real axis belongs to the root locus if the total number of real poles and zeros to its right is odd. This is called the real axis rule. Segments of the real axis that satisfy this condition are part of the locus. Rule 6. When the number of poles exceeds the number of zeros, the extra branches approach infinity along straight-line asymptotes. The angles of these asymptotes are given by 2q plus 1 times 180 degrees divided by n minus m, where q takes values 0, 1, 2, and so on. The asymptotes all radiate from a single point on the real axis called the centroid. The centroid is the sum of the pole locations minus the sum of the zero locations divided by n minus m. Let us plot the root locus for a simple example. G of s equals 1 over s times s plus 3. There are two poles at s equals 0 and s equals negative 3. No finite zeros. Two branches start at the two poles. The real axis segment between 0 and negative 3 is on the locus. The asymptote angles are 90 degrees and 270 degrees. The centroid is at 0 plus negative 3 divided by 2, which is negative 1.5. The branches break away from the real axis at negative 1.5 and go vertically to infinity. The breakaway point is where two branches leave the real axis and become complex conjugate. It occurs where the gain k is at a local maximum on the real axis segment. For our example, we can find it by setting the derivative of k with respect to s equal to 0. The branches break away at s equals negative 1.5, then travel vertically upward and downward along the asymptotes. The root locus is not just a picture, it is a design tool. We can choose the gain k to place the closed-loop poles at desired locations. For example, if we want the poles on the imaginary axis, we find the k value where the locus crosses the imaginary axis. If we want a specific damping ratio, we draw the corresponding zeta line and find where it intersects the. Now a slightly more complex example. G of s equals 1 over s times s plus 1 times s plus 2. 3 poles at 0, negative 1, and negative 2. No zeros. 3 branches. Real axis segments between 0 and negative 1 and from negative 2 to the left. Asymptote angles 60, 180, and 300 degrees. Centroid at negative 1. two branches break away near s equals negative 0.42 and eventually cross into the right half plane, making the system unstable for large K. This last point is critical. The root locus shows us the maximum gain for stability. When any branch crosses the imaginary axis into the right half plane, the system becomes unstable. The K value at that crossing is the stability limit. We can find it using the Routh-Hurwitz criterion applied to the characteristic polynomial with K as a variable. This connects everything we have learned in Lecture 4. Let us summarize the root locus rules. Branches start at poles and end at zeros. The locus is symmetric about the real axis. Real axis segments follow the odd count rule. Asymptotes have specific angles and a centroid. Breakaway points occur at gain maxima on the real axis. And the locus tells us the maximum gain for stability. With this, Lecture 4 on stability analysis is complete. In the next lectures, we will use these tools for controller design.